For as long as we can remember, humanity has dreamt of alien worlds. But what many don't realize is that alien life, more wondrous than we could have ever imagined, has dwelt within the depths of our waters for millions of years, evolving in all manner of eerie and odd forms, especially sharks, producing some truly alien looking creatures in the earliest millennia of their evolution. Some of these early sharks were so alien they looked almost nothing like sharks, with long eel-like bodies and sharp spines sticking out of their heads, that their names embody these alien traits. The Xenacanthus. Xenacanthus was a genus of shark that once roamed Earth's waters during the Carboniferous and Permian periods, possibly even the Triassic, millions of years ago, with over 20 species having been found around the world. Now, as we all know, sharks are old, and I mean really old, as in millions of years old, and Xenacanthus is one of the oldest, in a very long natural history, with the oldest fossils dating back to over 300 million years. That's older than the dinosaurs. In fact, it's older than most groups of vertebrates, period. Contrary to popular belief, sharks haven't survived unchanged for millions of years. Quite the opposite, actually. Throughout the span of millions of years they've been around, they've diversified into a countless myriad of forms, niches, and environments as they've continued to evolve and change throughout these past millions of years, carving out their own unique corners of the fossil record, many looking almost alien, especially compared to the sharks swimming around today. And Xenacanthus exemplifies this principle especially. So alien, in fact, that it derives its name from its odd appearance, with the name Xenacanthus meaning alien spine, in reference to the large spine sprouting from the shark's back. This distinctive spine is one of the defining traits of the group the shark belongs to, the Xenacanthids, or Xenacanths for short. A group of sharks that share the very same eel-like body shape and dorsal spines that Xenacanthus has. While not ancestral to modern sharks by any means, they represent some of the earliest forms these fish took at the dawn of their diversity. As odd and out of place the spike may look on these fish, it's surprisingly common within the natural history of sharks, from hippodontid sharks having similar spikes over their dorsal fins, while possessing a more traditionally shark-like body plan. Even today, modern species can be found inheriting this bizarre feature, found specifically in modern horned sharks. It's this modern species of shark that may give us a clue as to what these spikes were for. The spikes of horned sharks are foremost a defensive feature, acting as a passive and defensive measure, deterring predators from attacking from the risk of getting stabbed, or preventing large predators from swallowing them whole, with their fin spines stabbing into attackers and causing the larger fish to spit them out. Xenacanthus may have been using a similar strategy with its so-called alien spine, especially when you consider it was far from the largest predator in the Carboniferous swamps. The world Xenacanthus dwelled was almost as alien as it was. In fact, it looked like an entirely different planet back then. A lush human world whose vast horizons were blanketed in endless rainforests of giant ferns instead of trees. In the place of calls of birds, these forests were filled with the buzzings of giant insects and the echoes of giant amphibians. And Xenacanthus was right at home here. Xenacanthus didn't live in the sea. Instead, they preferred to make their homes within the swamps themselves. Here, giant amphibians and tetrapods dominated these waters, along with several giant fish, including other larger sharks prowling the swamps. This is where the spikes became very useful, providing the smaller sharks a means of defense in these murky waters, preventing any would-be greedy predators from swallowing them. or at least taking their attackers with them in the process as they struggled and stabbed on the way down the gullet. Talk about a hard pill to swallow. Dorsal spines aren't the only thing Xenacanthus has in common with modern horn sharks. Incidentally, they also lay the same type of eggs, with preserved fossilized xenacanth eggs showcasing the same spiral correlate found in horn shark embryos. But this is where the similarities between the two come to a close, as we begin to realize the spiral eggs and fin spikes were the least alien things about these sharks. What's truly alien about Xenacanthus and its kin is that they didn't really look like your average shark, even from a distance. With the body plans of these sharks having flat, elongated, eel-like builds, instead of your usual shark, and probably swam in a similar manner to eels. The sleek and slimy body of Xenacanthus wasn't the most optimal for fast swimming, undulating its entire body side to side in motion as it swam through the water. It's an energy-efficient method, especially compared to the rapid swishing of caudal or tail fins to generate thrust, but it comes at the cost of moving very slow by comparison. Fortunately for our Xenacanth, that's not an issue. After all, if you're a bottom dweller, you don't need to expend that much energy in a chase. Instead of cruising through the swamp and river waters, Xenacanthus would prowl beneath the lakes and bayous, hunting in the benthic zones to search for small prey like fish, invertebrates, and any carrion that floated to the bottom, with their preserved teeth indicating that these sharks were specialized in feeding on tough-shelled prey, which is expected for a shark living in a world dominated by arthropods. What's most remarkable about this is the way they went about hunting for prey, bearing specialized fins, potentially allowing it to walk beneath the water, bearing strikingly similar adaptations to those of epaulet sharks. Epaulet sharks use their strong circular fins to quite literally walk, both on the bottom of the seabeds and coral reefs, and even walk on land for brief periods, in order to move from one area to another, both for foraging for food and the moving of shifting tides on their coastal reef homes, in particular due to the low oxygen of tidal pools that they're stuck in. It's distinctly possible that Xenacanthus could have operated under the same pressures. Of course, the Xenacanths moving on land is only speculation, with the only evidence that we have being that the limbs could have been used to walk beneath the water. However, Xenacanths were nevertheless adaptable animals, with evidence suggesting that even if these animals weren't walking on land, they lived in radically different environments throughout their lives, with isotope analyses of their teeth suggesting that some genera like Orthocanthus were living in both coastal and inland waters with varying levels of salinity, most notably at different ages of their lives, similar to salmon, migrating inland to reproduce and lay their eggs, where their young will be safe from sea-going predators. Whatever Xenacanths were doing, it was certainly working, and at the very least would have been useful in the changing tides ahead. In the midst of the Xenacanth's rise, the Carboniferous came to a close, with the global swamps and rainforests diminishing dramatically due to the climate beginning to dry, and the oxygen in the atmosphere beginning to decrease due to the diminishing rainforests, resulting in the decrease of diversity of giant insects and amphibians that heavily relied on these environments, while early mammals and reptile ancestors began to rise to dominance, being less reliant on the conditions of the Carboniferous. Surprisingly, or rather unsurprisingly because it is a shark, Xenacanths managed to survive these changes, with Xenacanthus itself managing to persist into the next era known as the Permian, where this genus would live alongside many early land vertebrates in the drier climate. It wasn't until the end of the Permian that this group of sharks would experience a tremendous decline, being some of the many major casualties of the Permian mass extinction that wiped out nearly 90% of all biodiversity on the planet, rightfully being called the Great Dying. But even the Great Dying was not enough to wipe out these hardy alien sharks, with xenacanths managing to survive and cling on to the very earliest days of the Triassic, before they went extinct entirely, just before dinosaurs began to appear. It's a bit of a debated topic on when Xenacanthus itself went extinct, due to the number of various species classified within the genus, with some experts suggesting that Xenacanthus managed to survive to the early Triassic, while others suggest that the xenacanth remains from the Triassic layers represent their own distinct genus called Moriodontus. While it may not have survived to the modern day, Xenacanthus represents how far sharks have come from their earliest alien beginnings, and most importantly, their incredible diversity and adaptability throughout the ages as they continue to evolve into the sharks we know today. And most importantly, they represent how even the most alien of organisms come not from the stars, but from the alien worlds of our past.